Okay. Okay, now we are going to learn on the polar coordinates and the polar curves. Okay, so how we are going to work on the polar is basically we are going to write the coordinates based on the radius and the angle. Okay, so this is just an example how the radius will be applied in the polar system. When you have radius equal 1, means that we assume it's applied for all possible angles. So when we have r equal 1, our curve becomes this circle here. When we increase r equal 2, this will be another circle. So it means that r equal 1 is a circle with radius 1, r equal 2 is a circle with radius 2, and so on and so forth. Now to be precise, for example, let me precise this. If you want to, maybe you want to make something on, let's say here. So this is some angle, okay, some angle theta. Now we could write on this point is r, our r is 2, comma, theta. Theta maybe, let's say, if that is pi over 6, for example, or pi over 4, we could write here that this point P, this point P is 2, for example, pi over 4. Okay, if theta is pi over 4, and so on and so forth. That is how we pinpoint our coordinates in polar system. Okay? So you get r and theta. So that means for every possible coordinates, the r will be always positive. Right? Well, of course, in trigonometry, we know that there are some that makes negative, right? So how do we make it into this system? If we have an equation, let's say sine maybe in the quadrant 3 or 4, maybe sine 3 over 4 pi. That's negative, supposed to be. But how do we write? So it's gone from here. How do we write if something is negative? Radius is negative.
It cannot be.
It can. But how do we write? How do we pinpoint the negative? Here.
It's outside.
The angle from the origin down to.
You could think. You have the equation. Okay, you have a polar equation. The equations could be negative. The radius could be negative. How you write negative is you write in the opposite direction. We are going to see how that might be in the, I think later. I will show you how to graph the polar curves. Okay? Because sometimes we are going to have a negative and you will confuse. How do I write the negative? Okay. It could be understood as, let's say, let me give you some example here. Okay, so let's say we have a polar here. Just a few examples to see. So if I have, let's say this is the point, this is r, this is r theta, and let's say we have an angle here, which is theta. And then we have the other angle here, which this is going to be the difference between these two will be pi, right? So the whole angle will be theta plus pi. This is the negative. Okay. So for example, if there is no negative, you know the number, oh, it should be here. But since it's negative, oh, I should go here, okay, with the plus pi. But when you plus pi in your trigonometric system, you move the, for example, the sign is positive when it is in the first quadrant and the second quadrant. If you plus pi, it will shift through the third or fourth. Okay, got it? Remember that in trigonometric you have four diagrams like this, right? 1, 2, 3, 4. Right? Sine will be positive 1 and 2. Right? Cosine is 1 and 4. And if I ask why, I hope you should be able to answer that. Can you answer? Can you answer? Why? Yes, it's related to the how we deal with this. Oh, I already write here. Okay. It's related to this. And then you will see that here is all positive because the x and y is positive. Here is y is positive, x is negative. Here is the negative, negative. That's why the tangent will be positive here. This will be positive, y is negative. Okay, so there will be some combination of that. And from that perspective, if we shift pi, let's say from 1, we shift pi, it will move, right? It will be moved at least, if from here, it will move through 3. Right? If it's through, maybe it's moved to 4, if you plus pi. That's why, when we plus pi here, that's how we get our negative radius, okay? Later I will maybe practically how we find when we sketch the curve. This is just how to see where is the negative on the polar system, okay? I think I will just go directly to and one more equation that is important is the circle, which is the x squared plus y squared, okay, equal r squared. Okay, all these equations, the purpose is to convert the Cartesian to polar, okay, or polar to Cartesian. Okay, I think there are some examples here, but I think not important. Okay, so if you have an equation, for example, equation of the polar, we can write the polar equations like r equal function of t or function of theta. Okay, so if you have r is a constant like 2, we can just draw a circle with radius 2. We could also write an equations that is and theta, maybe theta equal pi over 4. So theta equals pi over 4 means we would have a single line which denotes the theta that is going to be infinite line as long as that is pi over 4. Okay? Hope you should get it. Or you could see that is related to our tangent, which is this is y over x, our gradient. Okay? You could also compare with that. Okay. Now the important one, however, okay, I think, okay, if you want to write these notes, but I don't think the important thing. I think the conversion and this one. I think this one and this one should be. Now the complication with the polar is because you are familiar with the Cartesian, it is a little bit strange that you are going to move the perspective from Cartesian to polar, okay? Especially if you are dealing with the integrations. Usually you deal with the integrations. For example, we have the, let me just write in the board. Let me just write here. If this is x, this is y. Let's say we need to compute the area in between these two curves. We know exactly that the top minus the bottom curve, right? And that will be the area between these two curves. In polar, there will be no y and no x. So we are going to compute the area between curves based on the angle, okay? Which one is first, which one is the last one, okay? That will be, sometimes you need adjustment to get familiar into, and it quite a little bit confusing at first. Okay? But if you know how and you have experience, it will be okay. Okay, let me continue. Okay, now sketch the curve with polar equation r equal to cosine theta, and then find a Cartesian equation for this curve. Oh, we have the table for all the special angle values. So we have 2 cosine theta. So when theta is 0, cosine theta is 1, so it should be 2, etc. Okay, and you get all the special angle values converted. And this is to help to map our sketch. So I will explain slowly here, one by one. So we could try to pinpoint all the directions and all the angle and the value of the radius. So usually we start by taking this line. Okay, remember now this line is not x and y. Okay, this is just an additional lines to help sketching the polar curves. Okay, now we start from here, which we call the polar axis. The horizontal line is always the polar axis. Okay, now we start from the angle 0. Okay? So we start from 0. 0 has a radius 2, so you can just make a proportion. Maybe 2 is here, so 1 is here, so maybe 2, maybe around that. So let's just do that. And maybe here is 2, 0. Okay, so r theta. Okay. And then suppose it is increasing, so we move pi over 6, okay? And pi over 6 is around square root of 3, and I think you can simply approximate square root of 3 in decimals to make it simple. And maybe it's around here, and then you move on to the pi over 4, square root of 2, maybe pi over 4 here, maybe it's going there, and then pi over 3 is 1. So if 1 is here and here, so maybe pi over 3 is going to be around here, somewhere around here, okay? And after pi over 3 is pi over 2, which is here, right? 0, pi over 2, pi, 3 over 2 pi, and then back again 2 pi, right? So pi over 2 is back to 0. So it's actually, it's going to be this point, okay, and then going back here, right? So just to help you navigate, so we have this point here. Let me just write, this is 0 pi over 2. Okay. Maybe if this is 1, this is 1. This is probably maybe here is the this is just for helping. Okay, this is going to be this is perfectly here. This is, I think my proportion is a little bit off, so let me this should be a little bit higher here, maybe here. Okay. And now, after pi over 2, we move to the 2 pi over 3. Or in degrees around 120. So 120 is about here, right? So after we get pi over 2, we should get around here, which is -1. Remember, it should be around here, but since it's negative, we move here. Okay? Get it? Okay. So this should be symmetrical with this, and this is also the value is equal to, okay, with the 1, so this will be around here. So this will be -1, 2 pi over 3, and this is perfectly fit with our previous statement that if we add pi, or if we add pi to this or this, it will be the negative version of the radius. Okay, so that's why we write here. It should be around here somewhere, but this is perfectly the opposite direction of our original point. Okay, I hope you get this point here, and do the same thing with this, and you will see that this will be symmetrical. So all this will be symmetrical. This will be symmetrical, and the endpoint is here. Okay, at this at 2 pi. So I think I will just make conclusions that this should be a. I hope it's fit. If not, then I will adjust. Oh wait. Yeah, I think it's fit. Yay. Okay, so that's how we get. Okay, so this is our curve R2 cosine theta, and this is how step by step you write or sketching the curve. Okay? You start from the polar axis, start from the angle 0, and then you could use some values maybe in between, and then values for the pi over 2, pi, 3 over 2 pi. This is, I think, the four angles, 0, pi over 2 pi, and then 3 over 2 pi. That will be very, I think, the very foundation of the first sketching, okay, for your polar curve. Okay, so all these 4 corners will be, I think, you could start from that point, okay, to see how your curves will end this. Okay, so that is the 2 cosine theta. Now, if you notice, this is cosine. If you do the same thing with, let's say, 2 sine theta, it will be the circle, but it will have different points. Because sine and cosine, they will have a complement with each other, so we suspect they will be another circle with sine. And if you try to see, or let me just give this shortcut to get to know, and then you can check whether that is correct or no. This is 2 cosine theta. Okay, let me just give you a small picture on the right side here to help you to get everything for this. And this pattern will always be the same for all polar. Okay, so let me just give you directly what it is. Okay, so first is you get here, right? You get this. Okay, this is 2 cosine theta or cosine theta, any constant. Here, this is the, so this is R, let's say A cosine theta. A is for any constant. And this will be R negative A cosine theta. Okay. So A cosine theta here, the negative one will be here. And it will perfectly fit because you just what you need is just to multiply with negative, and you will see, you will mirror through the vertical line. Okay? You can check that out. But this is the conclusion from all polar curve that you might encounter. Okay? The cosine here, negative cosine here. What was sine? Sine, you will get the positive on the top, the negative on the bottom. And it will work for all combinations in terms of polar curve. Okay? So let me just write again. Let me make line a little bit longer here. And then maybe here, the line. Or maybe here. So let's say we are having the green one. Okay, now this will be R, A sine theta, and this will be R negative A sine theta. Okay, so this will be fit, or it works for all combination of polar. Okay, so for cosine or sine, that's how we are going to work with. And you could check like the same idea, step by step, taking all the small points. You could also do the same thing for the sine, or for negative sine, and for the negative cosine, and see whether it's correct or not. Okay, now one more sketching curve just to show you. So all of this are this is the basis, the foundation, and this is one that might encounter. So this will be a very generic standard polar curves, which we call the cardio. The cardio. Cardio as in the cardiovascular, or cardio in your heart. But the shape should be similar to hearts. Okay? So sketch the curve R equal 1 plus sine theta. We could map one point, like a special angle value that's easy to count. And to help with that, I have this as in the value of R, different value of R. Okay? Just to help out for sketching the curve. Right? So this is graph R as a function of theta. So we now have the, when theta is 0, R is 1, so sin theta is 0, right? And then sin theta is pi over 2, it will be maximum. So 1 plus 1 is 2, and you see all changes through here. And we are going to map all these changes, all these points, through our polar curves. Okay, so let's try that out. Oh, by the way, I forgot. If you want to find the Cartesian equation for this one, what we can do is we can let me just write here. We have x equal r cosine theta. I forgot to mention this. So cosine theta is x over r. So r equal to cosine theta. This becomes r to x over r. And then this gives you 2x equal r squared. And then this will be x squared plus y squared equal 2x, or x squared plus y squared minus 2x equals 0. And then you can check the standard form. You will see that this will be a circle equation shifted. The center point is shifted to the right. Okay. Okay, now back to this one. Now we need to sketch the curve. Now we could start from, let's say here. So let's say we start from 1. Okay, so 1 is here. This is 0, 1. And then pi over 2 is 2 here. So it should be a 2, pi over 2. This one. And then you are going to see how much the movement from this line, okay, let's say you try to, like, you get maybe pi over 6, pi over 4, pi over 3, you check which point here that is corresponded with the r value, and you're going to see that from this point you will see a little bit slightly goes here and then moves to that point. So you will get, let me write with the right color. So you will get that this will be, okay, like that. Okay. And then the same thing, you check from pi over 2 to pi, it's getting, you could try your best using calculus 1 definition for the tangent, the slope. But I don't think you remember, but so I just skip that. so you could just like pinpoint some special values. So you see it starts slowly and it starts fast. So it will start slowly like this one, and then fast and then go down. Okay, so it will be going that, and you can check when pi is here, it's perfectly equal to 1, okay? For theta equal pi. So it's equal 1 here. Or in our case, perhaps, maybe this is not a good proportion. Let me make it clear. Maybe here, the 1 is here. It's not good. Yeah, suppose that is okay. So this will be pi. So this this is pi over 2 pi, and then this will be 0, 3 over 2 pi. And then notice that at 3 over 2 pi, it goes to 0. So from this point, so we move, okay? We stop here, and then when we try to move again, before we cross this, it's going to be 0. Okay, so it's going to be moved that way. Okay, so we have that line. So let's draw that. I think I will use green color here. Okay, And then from the 3/2 to 2 pi, this will be a symmetry, okay? The same what we did before. So it will be symmetrically the same with this green line. So it will be another one, okay? Another one. So 2 pi is 1, right? So back to the original point. So we are going to say here will be that will be the cardioid. The heart shape will invert. And as I mentioned, see, sign positive goes up. So in terms of cardioid, you will see the large part is on the top. So you will know if you have 1 minus sign inverted. Okay. If you have 1 plus cosine, okay. You have 1 minus sign, minus cosine will be on the left. Okay. So that is the pattern. Okay. The same pattern we discussed previously. Okay. So this is the R, 1 plus sine theta. We call this the cardioid. The cardioid or cardioid. Or maybe let me finish the last one here. You can write here as okay. So cardioid. Now the next curves that we are going to see a lot in exercise are the one that called the rose. Rose as in flower. So we can like sketch like a flower. Okay. So let's try to see that. Okay. So this is the rose curve. Okay. R equal cosine 2 theta. So this is the R value, similar to what we had before when we sketched the cardioid, to help us create the polar curves. Starting from theta equals 0 is 1, okay, and then starting to going down because the pi over 4 makes the R 0, and then afterwards it will be negative and still negative, and then it's adding to 0 again, and then it's positive, and then negative, positive, and so on and so forth. Okay, so we are going to map this into the polar system. Okay. So we start by taking the polar axis and a vertical line to help. So this will be theta equals 0, theta equal pi over 2. Okay. Now start by taking maybe 1 is here. I think I will use red color here. That is 1. We are going to expect that because pi over 4 is 0, so when we increase the theta, when it is pi over 4, it is going up there. Okay. So that is the first part that is on 0. Okay, that's the first part. Let me just add this as theta equal pi over 4. Okay. And then pi over 4 until pi over 2, it will increase to the max at radius 1 or negative 1 if you see this value. So it's supposed to be from pi over 4 to here, right? Supposed to be this, but since it's negative, it's here. It's going to be, okay, you see that? I hope you see what I've been doing here. So it's going to be okay. So this is 1, this is also 1, or negative 1 if you would like to write. But maybe just 1, okay, easy to follow. Okay, and then from pi over 2, we are going to 3 over 4, which is 0. So we are going to, again, we see this is actually from here, but since it's on the negative part, this is on this side. So we move through that. Okay? It's a little bit confusing, but I hope you get it correct. Okay? I hope you get it correct. A little bit confusing, but okay. And then we move, so that's 3 over 4. Let me write 3 over 4. The 3 over 4 is actually here, but the result, since it's negative, is going here. Okay, here in this part. Okay. Okay, now back to the positive, which is we move through this 3 over 4. Okay. We move on through the pi. So from here, we move through pi, which is pi is the maximum now. It's 1. So it's going to be like this. Okay. Back to the original track, okay? Not the negative tracks, right? So we move again here. Let me write here. This is 1. Okay. Until the pi is 1, and then back to 0 again when it's 5 over 4. 5 over 4 is around this quadrant, right? So it's going to be this 0, right? Okay, and again, since this is just pi over 4 plus pi, which is the same with what we have before, the negative and positive. The difference is pi. So when we plus pi, it's 5 over 4, right? 5 over 4. So this is 5 over 4. So the same line with the pi over 4, right? So that is just to give you an idea. Okay, after 5 over 4 pi, we increase again to 3 over 2 pi. So we suspect from this line, we need to go here, but since it's negative, it's go here. So from this, and then go up. Okay. So it's supposed to be okay. Okay. So it's actually quite fun, right? So it's going to be here until when it's reaching the negative 1, the 3 over 2 pi is going to be here. Because it's negative 1, right? And then the same thing, going that way for that until it's 0, 7 over 4. 7 over 4 is the same line with the 3 over 4. Because 7 over 4 is 3 over 4 plus 5. And then back to the reality. Okay, and then you get back to this. Okay. So if you just read the textbook, see the picture already with the direction, you will confuse how to deal with that. So this is how actually you go the polar in the rows. And then it can be increased. The number of the leaf of the flower could be increased. Depends on the theta. It can be 3 theta, 4 theta, 5 theta. There will be some patterns, and I will maybe conclude later in the next part. Okay. Okay. So that's why the polar can be confusing. We are not done yet. This is not the calculus part. This is the intro for polar.
What would be the effect for another scenario?
Yeah, I will tell you like the whole conclusion. Yeah,
and look at it depends.
Yes,
So,
yes. You can imagine like that. Correct. Yeah, so it's interesting, right? And confusing at the same time. Interesting and confusing at the same time. So I will give you a conclusion and what to expect, at least from the polar curves perspective, is from the very basic we have the circle r equal a constant or a sine theta, a cosine theta, or a spiral. Okay, that's the very basic. And then we have something called limaçon. So limaçon is basically something that is intertwined, or there is something having loop. This is cardioid, the one that we have done before. So basically cardioid is you have a plus minus b sine theta or cosine theta. So if a equals b, then it will be cardioid. If a is less than b, so this a constant a less than b, we would have a loop. And then if you have a greater than b, but not so over this 2b, we have a dimple. Okay? And then after that, we have a convex. And you will see that as the a going to be greater and greater, it will be getting closer to the circle. Okay? It's getting closer to the circle. And there is roses that we have done before, the cosine 2 theta. So every even number of roses, for example, 2 theta has 4 theta. So for even one, we are going to multiply by 2. Okay. For example, for 4 theta, we will have 8 leaves. Okay. But for the odd one, it is the same with the numbers. So for example, 3 theta, we have the 3 leaves. Okay. If we have 5, we have 5 leaves. And the last one is lemniscate. Not much talking about this, but this might appear in the exam or in practice. What you should remember is the lemniscate is like an infinity. It has r squared, a squared cosine 2 theta. Okay. But don't worry, in exam I will also put the picture to help you to navigate. So it's still difficult. But for practice, you could try the questions from scratch. It means you need to try to draw first and then try to find the solution. So all of this as a conclusion for the basic curves in polar. Okay. Okay. Any questions? So this will be the introduction to the polar curves. Not yet in calculus yet. So the expectation is that, for this one, you will see how to find the area or how to find the tangent. But most likely for this curve, maybe the question that frequently asked is the area. You see that it has a small loop here. What is the area of the small loop? Okay, we are having a break, and we are going to continue later on. After some time to elaborate the polar curves and how interesting it is and how strange and also confusing at the same time, we are going to look for how to evaluate calculus part in the polar system. Okay, so before we go through each one of them, so what I would like to start with is, since we are going to have a, let's say, so most likely if we have a curve that is in polar, usually, maybe if we take an example like a circle like this, like if it has this circle, and then if we slice the circle, for example this one here, and having some angle here, and of course if we are going to imagine this as a, let's say like a pizza, this one, then we could find the area. Okay, the area of sector. Say this is the area of sector. So we could write this. So this is what we call the sector. And how we find this area is basically that the angle divided by the whole circle multiplied with the area of the circle, which is the pi r squared. This will be equal to half r squared theta. Okay. And this sector, this is a good way to represent how the area in the polar curves will be defined. Okay. So if we have a random area here, let's say this r is function of theta, and we have a random curve on that, and we define that this area in polar system are closed by this theta equal a, and until theta equal b. So now we are going to have this endpoint, okay? A to b. Okay. And then let's slice all the area. Slice up, okay, all the area according to the center, which is the origin. So we're going to have this. Okay, so we slice small part of area. We slice like a, and it's like a rotating machine. Okay, and then we define this small area. Let's say we have some small angle we call theta I minus 1 and theta I. This is just to show that it's very small. And in the middle part here is a sample point, the theta axis. And then the whole thing here, we say that this will be the delta of the theta. So it's very small. Okay. Now from this part, maybe let me write here first. So polar curve is r equal function theta, and theta is let's say this will be in between 0 to 2 pi, because that is the maximum polar angle. Okay, so we divide AB into subinterval. So we say the delta theta is and then you could have the delta area. It will approximate half we are going to use the sector. The r is a function of theta, so let me write theta I asterisk squared delta theta. So the approximation of the total area, so approximation or approximately the area is going to equal or approximate the sum from I equal 1 until some n half okay. And then if we imagine the n could be larger and larger, so we cut everything on the area really small, it means that as n getting larger, or n is getting infinity, then let me write here, then limit, we could imply the limit this will equal integration from a to b of the half function of theta squared d theta. Or you could see that this equal to this. Okay. So very simple at the conclusions. Okay. But how to apply somehow, since it's in the polar system, sometimes when we apply this, it's a little bit confusing. Especially if the polar curve is not something that is well defined in a picture. So that's, I think, interesting and confusing. And sometimes all the concepts that we have learned in the graphs, like symmetry, maybe it will be useful because most polar, it has symmetry. So it can help you to, at least for calculations, okay? To avoid mistake in numbers, you could try the symmetry, and then like if it's like you have a half part, then to get the full part, you can just multiply by 2. I think it could be useful. It could be helpful, and it could help you to navigate through all the curves in the polar. So the symmetry. We're going to see later on. Okay, I think we can move to the next page. Or maybe any questions first? How is your TA, by the way? Okay. If you have any suggestion, let me know. Okay. Okay, I will move to the next page. Is that okay? Okay. Just a quick example. Okay. This is what we did. The roses for cosine 2 theta. Okay. We would like to know this one loop, like how much the area for this one. Can we evaluate the area for one loop of the roses? Sometimes in the fourth quadrant, we can just write the negative of the first one, the first quadrant. Or if you would like to write the complete one, maybe you could write 7/4, this one, the same thing. But usually, my personal take is just make this negative pi/4. I think easier to compute. Okay. Okay, now let's write down the formulation that we have. So the area, let me just write what we have before, is integration from a to b half r squared d theta, right? R is cosine 2 theta. Or let me write, this is okay, and then this will be half cosine 2 theta squared d theta. Notice that in polar, there will be a lot of algebra part for trigonometry. So I hope if you have ever seen this part like this, if we square, this will be cosine squared 2 theta, right? So remember, every cosine squared or sine squared, the best way is just to take the double angle. So make it through double angle formula. Let me write the standard double angle here. Or maybe let me write the complete one. Start from here. So if it is having a cosine squared 2 theta, so we are expecting there will be 4 theta. Okay. So that way, we are going to have and another suggestion is that whenever you have this, okay, this is something that me personally, I would like to avoid this, because if we take this at the end, maybe in your calculations, maybe there will be some mistake in this in the signs, maybe some mistake. So what I personally like is we take this into two parts, 0 to pi/4, and multiply by 2 because it's symmetry. Okay. So we can write here. Due to symmetry, so we can write that the area is 2 times
or let me write maybe cosine squared to theta, maybe just directly that. So this will be cancelled, and we can compute cosine squared to theta, and we can convert that through double angle formula. So half plus cosine 4 theta over 2. And then take integrations. Sine 4 theta. 2 by 4 is 8, or 2 by 2. Yeah, it's 8, right? And then input 0 to pi over 4. I think if we input 0, all 0, right? So we are going just to write the pi over 4. And pi in sine is also, we can ignore. So this will be pi over 8. Okay, so for this case, I think not many calculations and process. Okay, any questions from here? If you see this writing,
Take out the
this one is from here, right? And then I make it into 0. Half part. So I multiply by 2. Okay.
Okay, let me move through next example. So I would love to like have a small example, move to the next one, and then at the end of the subtopics, we are going to have like all exercises. Okay. Okay, now this is another wait. Another
Example or a typical questions that maybe work in exam. So sometimes you will have two different polar curves, and they will have some intersections with one another, and your goal is to find whether the for example here is you have the circle here, 3 sine theta, and you have the cardioid 1 plus sine here. It has this intersection here, which usually you can find by solving the polar equation, and then you get the theta. And the question is asking the region inside the circle, but outside the cardioid. So outside cardioid here, inside the circle. So this blue.
So we've done an area of the circle minus the cardioid area.
Okay, so the cardioid is here. The circle is here. There is some area that is over. So if we try to minus, we might get the whole area here, which we can find through the 3 sine theta from 0 to pi perhaps. And I think that will work. That will work. I think that will work. Yeah, I think that will work. And this 1 plus sine from 0 to 2 pi. Yeah, I think that will work. We can try.
But I would like to start with the intersection is start from pi over 6 to 5 pi over 6. Okay. But I think if you're just subtracting the circle to cardioid, you will missing some area. So this could be done by finding the intersection. So this is intersection. So to find the intersection, you could take the 3 sine theta equal 1 plus sine, which is equal to 2 sine theta equal 1, and sine theta equal 1 over 2. So you could find how many theta that is going to be positive 1 over 2. We get the pi over 6 and pi over 6 pi. So this will be pi over 6 and 5 over 6 pi. Okay. Since we have this pi over 6 and 5 over 6, we could write the area is half
If we focus on the circle, if we want to compute the circle from the pi over 6 through 5 over 6 pi, this one is the area, right? You see, perfectly this here, from here, okay? So
let's write that as the first one. So half of 3 sine theta squared d theta. Okay.
And that, we could take the cardioid exactly the same from this to that, okay? And that will be perfectly fit, okay? If you just subtracting the whole thing, you will have this that is not in the area, okay? So, my idea is all from the point pi over 6, all circle and cardioid, they have the same intersection here, right? So here
is the fourth circle, and this one is for the cardio. So I think let me just draw in here. Let me write first. So this is from the circle. So this is 3 sine theta, and this is the small one. I think make it smaller. Okay. This is 1 plus sine theta. So we are going to minus this green one area to this red area. So we get this shaded here. Okay. Now it's clear, right? What happened here? What happened with this whole one? Okay. And again, how we works based on the polar is from here. Okay. Something like that. It starts from 0, and increase the angle, increase the angle, something like that. Okay, I think we could just finish the integration, evaluate. And of course, if you want to use the symmetry, you could do symmetry. It's mirror right and left. So you could say pi over 6 to pi over 2 and then multiply by 2. The same thing with the previous one. So we could make that happen. Because I think this one may be a little bit tedious, and maybe you could have some mistakes doing that. So we could make symmetry. Okay. So due to symmetry, we could write, and I will expand the squared. So area is twice of or maybe let me write with the whole thing in brackets first. So half pi over 6 pi over 2. This will be 9 sine squared theta d theta minus half this is 1 plus 2 sine theta plus sine squared theta d theta and a close brackets. And since it's the same integrations, I think we can mix both, right? We can mix and then canceling the half and 2. So this 2 can cancel with this. So area pi over 6 pi over 2. And this will be 8 sine squared theta. And then minus 1 minus 2 sine theta d theta. Okay. Next is taking the double integral, double angle for the integrations. So we have here is 8 multiplied with half minus cosine 2 theta over 2. So area that will be 8 over 2 is 4, so this will be 4 minus cosine 2 theta over 4, right? So minus 1 minus 2 sine theta. So this will be 3. Hey, why I'm writing 4 down here? Should be here. So minus 4 cosine 2 theta minus 2 sine theta and then d theta. Okay, I think we are nicely done and we can nicely integrate all of this. So this will be 3 theta and this will be sine 2 theta. 4 divided by 2 is 2, right? And then plus 2 cosine theta. And then plug in pi over 6, pi over 2. Okay, I think 3 pi over 2, 0, 0, right? And then minus pi over 2. Pi over 6 is 2 sine pi over 3 plus 2 cosine pi over 6. They are cancelling, right? Sine pi over 3 is the same as cosine pi over 6, right? So it should be cancelling. So we can cancel. So we get that. We get pi for the area.
I hope you are able to integrate this. I mean, individually. I hope. So the idea is the trigonometric integration for cosine, sine, and then the double angle formula to help. And mostly that is our calculation in integration for the polar. Mostly that is the calculation. However, the main difficulty is not this calculation. The main difficulty is to make this one. How to take the endpoint, which one of them, and how to imagine which part of area that we want to evaluate. That is, I think, quite difficult, especially if you are not familiar with the polar system. That will be very, very difficult, I think. So I think you need to be familiar with the polar system. Always start from the polar axis, and then you can navigate through the rotation. Okay.
In these cases, when these kind of exercises are used, would we have a graphic sketching or should we sketch?
For exercise, sometimes not. For exercise, sometimes not. So you need to draw.
Draw it first and then start doing.
Sometimes, if you know how, you can directly write. But for some unknown graph, then maybe you need to try to sketch. But I think mostly for exam, I think I would just give the picture. For exam, but for practice, you can some of them need to sketch first. But some exam, like a few of them, like for that easy graph, I'm not really giving the picture for the easy one. I'm considering the easy one as the cardioid and the circle. That is easy. I think the difficult one is the roses and then the loop. Actually, there are some, I would say like a shortcut how to draw really fast, but I think you could find on YouTube. There will be many of them.
Does that technique have a name?
No, you're just googling polar curves tutorial. There will be many of them. I already watched like most of them and I know how, but I don't have time to teach in class, so I think you can just watch them.
Anyway, before we move to the arc length of the polar, I think there are some illustrations that maybe generalize what we have here. So what we did is actually we have let's say we have a polar. We start from this. Let's say this is a theta equal A. And then we have another theta here. Let's say this is theta equal B. And then we have a polar which perfectly aligned here. That's it. That is the first one. This is the second one here. Or maybe different color. Let me write clearly. This is the first one. And this is the second one. Okay. This one is r equal f of theta. This one is r g of theta. And in between of them, we might have an area. Okay, so this is the area in between. So it's similar to what we have in the calculus 1, area between curves, but now it's in polar. Okay. So we might to write the area of this as, let's say, area A to B. I will write first the formulations. This is half, and exactly the same thing. d theta, and then minus the g. So this actually, if you imagine the f theta, the sector or the area, this should be the area. Okay. And the area for the second one is this. Okay.
So this minus this, that will be the area. Okay. So now I hope you understand that this f theta minus g is not because that is on the top, this is on the bottom. Not because of that, because of the whole area in the polar. So this for the green one minus blue, okay, the blue one. Okay.
Yeah. Oh, zoom out.
What do you think so far? Yeah, it's already out. I mean, we have set from this. Yeah.
Like, I think from like previous say, I said anything. So I think you need to change or check the is that the correct if you check through Moodle, I will get it. If you check through Moodle. If you say yeah. Or if you want to email me, use my email. I will reply as soon as possible.
In case like in case we cannot find it.
Okay. The idea is you need to define if the baby is negative output of the system. There is an outside. It is negative. But if we see here, it's not this that's what you understand that first. I'll back. Okay, the last part before we finish our class, I would just like to introduce the arc length and the polar, and then we can finish our class, okay? Just one more thing, okay, one more thing. So next week, we can review all and then have more exercises, okay? Or do you want to have exercise now? Because it's still new for area? Or giving new...
Can we focus another class on like lots of exercises?
Exercise from the previous one, right? Okay. So let me, okay, skip this. Okay, this is, let me put here. Okay, so this is all about the area. Which one we need to go? They don't even draw the graph for this. You need to draw by yourself.
They all look the same right now. They all look the same right now.
How about this 24? 24 is the cardio, I think easy to draw. Okay. Cardio number 24. I think since we don't have much time left, I think I will just try my best to work this number 24. So 24 is the cardioid and a circle. The question is, find the area of the region that lies inside the first curve. First curve means the cardioid and outside the second curve. Okay. So I think we might to draw this. Remember, if we have cardioid, but it's minus sign, so the big one should be on here, right? And this should be, well, it's not really good, but that should be illustrate how the r equal 1 minus sine theta looks like. Okay. And this will be equal to, the value is 1 here. This will be 0. Okay, now the circle r equal 1. So this is 1, this is 1. So let me write here. This is 1, this is also 1. So the circle should be intersect on that point. Maybe my cardioid not really good, maybe too small. Maybe let me make it bigger. So inside the first curve, inside the cardioid, but outside the second. So should be going to be this one. Okay. So if we want to find the intersection, we could find through this equation, right? R equal 1 and r equal 1 minus sine theta. We get sine theta is 0. So when sine is 0 is basically, we say 0 or pi. Or 2 pi. Since we are going to deal with this region here, which perhaps going to be the third and fourth quadrant, I think we better using the pi and 2 pi. So from pi to 2 pi. If you use 0, maybe it's a little bit confusing. Like, how can be 0 here, but this is area that we want to navigate, right? So we should write from pi to 2 pi. So pi and 2 pi becomes our theta. How much time left? So I think I will just write the area, not in a full calculation, just the area here. Supposed to be this. Half 1 minus sine theta squared. And since both are from pi to 2 pi, this will be that, okay, d theta, okay. And you could try to finish off the calculations. You will see that we have perfectly the cardioid. The cardioid we have from pi, which means this is going to be our cardioid, and minus 1, which is this one here. So the area is actually, the cardioid is this, and this one is this small one. Do you get it? Okay. This pi to 2 pi is here. You know, like you watch the anime Doraemon? The phone. Okay, I think that's it. Just you can finish off the calculation. Okay. Okay, that's good.